Hello. In this video, we will talk about the goodness of fit test. However, I want to start with this information, which is related to applications of chi-square tests. Believe it or not, there are a lot of tests that are using the chi-square distribution. This is quite a popular distribution in real-life applications. And you will see why. The chi-square distribution can be used for tests concerning frequency distribution. So answering questions such as, if a sample of buyers is given a choice of automobile colors, will each color be selected with the same frequency? And hopefully you see why we have this type of questions. What are the implications in the automobile business, right? The chi-square distribution can also be used to test the independence of two variables. For example, are senators' opinion on gun control independent of party affiliation? The chi-square distribution can also be used to test the homogeneity of proportions. For example, is the proportion of high school seniors who attend college immediately after graduation the same for northern, southern, eastern, and western parts of the United States? So we will go through examples of chi-square tests, all of these type of tests. And for all, we will be using what we know, 5 steps of hypothesis testing. We will do this using the critical region method or the p-value method. So let's get started with the goodness of fit test. Goodness of fit test, it's also called the GOF test. The chi-square statistic can be used to see whether a frequency distribution fits a specific pattern. This is referred to as the chi-square goodness of fit test, chi-square GOF. Keep in mind with this chi-square test, you will realize that we are actually comparing qualitative data. Up to now, we did a lot of quantitative data tests, and this is actually the part of statistics where we make inferences related to qualitative data. Assumptions. The data are obtained from a random sample, and you've seen up to now that randomization is very important. And then we have something new here. The expected frequency for each category must be 5 or more. So we are dealing with categories, and we'll be looking at frequency of values in that specific category. All of those should be greater than 5 or equal to 5. The formula for the chi-square goodness of fit test, this is the test statistic. It's based on the observed value and expected value. So the formula, this is something new. This is the first time we're seeing this formula. It's a chi-square. It's equal to summation of observed minus expected, which is squared, over expected. Degrees of freedom, because this is a chi-square distribution, we know we are dealing with the degrees of freedom. We need to know which chi-square curve to pick. But this time we see the degrees of freedom actually is number of categories minus 1. We have to figure out how many categories are we talking about and subtract 1 from it. O is observed frequency and E is the expected frequency. So keep in mind, to recognize this type of problems, you will need to have in one list the observed frequency, in another list the expected frequency. As we go through the examples, you will see what I mean. This will always be a right tail test because O, which is the observed minus expected, right here in the formula, this quantity is squared. So the answers will be positive or 0. Let's take a look at some other facts before we go ahead and solve some problems. It's very important to understand the meaning of good fit. When the observed values and expected values are close together, the chi-square test value will be small. And that makes sense, right? Then the decision will be not to reject the null hypothesis, which means there is a good fit. What's observed and what is expected are close together. When the observed values and the expected values are far apart, the chi-square test value will be large. Then the null hypothesis will be rejected. Hence, there is not a good fit. Now, for this test on the calculator, we have the command chi-square GOF test. So instead of going through the formula, which is a tedious process, we will be finding the chi-square value and the p-value using the GOF test. Here is our first example. A gambler drills a hole in a die and fills it with lead weight to produce a loaded die. The die is rolled 200 times with the following result. We have each outcome right here on the top, and we have the frequency for number 1, 27, number 2, 31, and so on. Use 0.05 level of significance to test the claim that the outcomes are not equally likely. So let's see, how do we write down the hypothesis? But first, we will write down the given information. Well, we don't really have too much. We know that the die is rolled 200 times, and we have the results right here. Okay, so I'll just say results. We can see those right here, and we need to use 0.05 level of significance. So the question is, test the claim that the outcomes are not equally likely. Test the claim, and this is the first time I'm not really using symbols because I don't really know how to write this down yet. Okay, I'll just simply write it down in words and then we'll figure it out. Okay, so let's see, first of all, why do we need to use a goodness of fit test? Well, this problem, it's about the frequency of outcomes. It seems that we have these results, and this will be, if you think about it, the observed results. So we deal with observed results, and they ask us if they are equally likely or not. So when we roll a die, we do expect equally likely results. So we see that we are dealing with a problem in which we have observed values. We have to come up with the expected values, and this is actually the first thing we should do. And then we'll go ahead and do a goodness of fit test. So let's do that. The first thing I need to see clearly are the two lists in which I will have observed values and expected values, and this will be actually the thing that we will do on the calculator. We have a list of observed values, and I will create a list of expected values too. If you think about it, what is expected to happen when you roll a die 200 times? You know, the probability of rolling a 1 is 1 in 6, right? The probability of rolling a 2 is 1 in 6, and so on, if we have equally likely outcomes. So when you roll it 200 times, you will have to multiply this by 200 to get the probability of getting a 1. So all of this will be equally likely. So the result for the expected will be actually 200 divided by 6 for each one of these outcomes. And this will be actually 33.33. So this is what I will actually write down, what's expected, and it will be on the next row right here. So the frequency of the expected values, rolling a 1, you will have 33.3. Let's just use one decimal. For 2, we will have 33.3, and so on. So when you deal with these type of problems, you should be able to spot or to create, if those are not given to you, like in this case, two lists. In one list, you'll have to put in the observed values. In the second list, you'll have to put in the expected values. So right here, we have observed and expected values. Now let's see, how do we write down the hypothesis? So the first step will be to set up the hypothesis. Setting up the hypothesis, it's based on the information given. So in this case, I can say that the outcomes are equally likely and the outcomes are not equally likely. To set up the hypothesis, we will simply write down that probability of getting a 1 is equal to probability of getting a 2 is equal to probability of rolling a 3, and so on, up to probability of rolling a 6. So these are equally likely, and that will be 1 over 6. And for H sub A, we will say at least one of these proportions or probabilities is different. So this is a right-tailed test, and the reading, the claim, that the claim is H sub A. So that will be the claim, and this is always a right-tailed test. Step 2, let's go ahead and write down the chi-square distribution. Chi-square distribution is the one that needs to be used here. This is a goodness of fit test. So to be specific, we are using the goodness of fit test, GOF, and this is a command that is on your calculator. And the degrees of freedom for this one will be number of categories minus 1. In this case, we have the number of categories, the number of outcomes, which will be 6 minus 1, which is 5. In order to find the p-value and the chi-square test value, instead of using the formula, I will be simply doing the test. So I'll get the chi-square and then the p-value, and then we can conclude this test. Let's go ahead and grab the calculator and do the chi-square GOF test. So the first thing we need to do, we need to get to edit, hit enter, and put the values observed in the first column and expected in the second column. So I have 5 numbers to put in the first column: 27, 31, 42, 40, 28, and 32. And I have 5 numbers in the second column, and these are all 33.3. After you completed this step, go back to step and go to test. I will go up because I know the chi-square GOF test is on the second screen. It's option D. So scroll up to option D and hit enter. And all you need to do is make sure you have your observed values in list 1, your expected values in list 2, and your degrees of freedom for this test will be 5, and then simply calculate. You get chi-square, which is the test value, as 5.87, and the p-value as 0.32. Keep in mind, you could have done this with a formula and with chi-square CDF to find the area for the p-value. However, since we have GOF, we simply use the GOF and we find these values. Because we're doing this using the p-value method, I'll be looking at this p-value and compare this with alpha. So at step 4, I will make the decision 0.32 and alpha 0.05, where it is clear that this is way bigger than alpha. So I will fail to reject the null hypothesis. And at step 5, I will say that alpha equal 0.05 level of significance. There blank enough evidence to, so keep in mind, we do not reject the null hypothesis, which means we have enough evidence to not support H sub A, which was the claim, right? So right here, we will enter is not, but alpha equal 0.05. There is not enough evidence to support the claim, okay? And this is how you conclude a goodness of fit test. Let's take a look at another example. A random sample of 106 car crashes are selected and categorized by age of the driver. The results are listed below. Age, under 26, between 26 45, 46 to 65, over 65, and these are the results, okay? The age distribution of drivers for the given categories is 18% for the under 26 group, 39% for the 26 to 45 group, 31% for the 45 to 65 group, and 12% for the over 65. Using alpha 0.05, there's the claim that all ages have crashes rates proportional to their driving rates. Okay, let's write down the given information. We have 106 car crashes. That's the sample size. And we have one 2, 3, 4 categories. So make sure we know that we have 4 categories. And let's inspect a little bit the problem. This is about a distribution that fits another distribution. They have the observed results right here. So this will be observed results in the first row from 160 car crashes. And this is the information they have. The age distribution of drivers should be this. Okay? And the question is, at alpha equals 0.05, test the claim that all ages have crash rates proportional to their driving rate. So in other words, we will try to do a goodness of fit test. Let's see, how do we go through all of those steps? How do we set up the hypothesis? The first thing I want to do, though, before setting up the hypothesis and do the test, I want to find a way to find the expected values. I know I need the expected values. If those are not given, I need to find a way to do it. Well, the expected values are based on these percentages. 18% should be what's expected in the first category. What do we mean by that? We mean that right here in this spot, we should have 18% of the total number. So what is 18% of 160? Well, we take the calculator and we find it, that's 0.18 times 160. And then by taking the calculator, we actually find what is expected for each one of these group age. So for 39, we will have 0.39 times 160. And then for 31, we will have 0.31 times 160 and 0.12 times 160. That's how we find what is expected. Okay, let's do that using the calculator, because anyway, we will be doing the chi-square GOF using the calculator. So here is the calculator. The first thing we do, we go to edit. Make sure you clear your lists, make room for the new values. And in list 1, we put the numbers 66, 39, 25, 30. In the second list, we have to put what's expected. Now keep in mind what's expected is given in terms of percentages. Do not put percentages in. You have to convert that to the actual numbers. So I will simply say 0.18 times 160 and hit enter. 0.39 times 160 for the second category and hit enter. 0.31 times 160 and hit enter. And the last one is 0.12 times 160 and hit enter. So keep in mind, we have values, numbers, numerical values, not proportions in list 1, and expected values in list 2. As long as I have this, I'll just write this down here: 28.8, 62.4, 49.6, and 19.2. Okay, and now I am ready to go through the 5 steps of hypothesis testing. Step 1, H sub 0, H sub A. Well, this is what we have as a claim. All ages have crashes rates proportional to their driving rates, meaning P1 is indeed 0.18. These are the rates. P2 is 0.39. P3 is 0.31. And P4 is 0.12, or the distribution fits the expected distribution. However, H sub A will be one of the P's is different. So you see the claim is actually this time the top one. We know this is a right tail test. This chi-square test will always be right tail test. Now we can do it using the critical region method. However, I will do it using the p-value method. So we are using the chi-square distribution. We have a degrees of freedom, which is this time 3, because we have 1, 2, 3, 4 categories. Minus 1 will be 3. And we will simply do the chi-square GOF to get the results. That's the fastest way of doing this. So here we go. Let's take the calculator and do the test. We have the values in list 1 and list 2. So all we need to do now is as simple as get to stats, get to the test, and for the chi-square GOF, hit enter. Make sure you have observed and expected, and make sure you have the degrees of freedom, which in this case is 3, and simply calculate. In this case, we have the chi-square from the calculator has a very large value, which is 75.10, and the p-value is approximately, and look at this, make sure you do not miss the e negative 16. It's a very, very small value. That explains because chi-square is a large value. So it will be 0.000, and I will not really write down 15 zeros to get to the first non-zero digit, but you can see that's a very, very small value. Okay, now we have these results. We are ready to conclude the test. Before doing so, I want to sketch the graph. We want to make sure that if we were asked to find critical values, we know that we need to use the chart. We know how to visualize this. We know that we have a chi-square CDF under distributions that will find p-values, but it's more convenient to use this chi-square GOF to get the results. But let's just make the connection with the graph. This is the chi-square distribution. Degrees of freedom for this one is 3. And this chi-square that we found right here, it's a very large number, 75. So that explains why the area associated with this in the right tail will be very small. So this is 75.10. And the area, this is the p-value, is very, very small. So we can just reduce it to 0. Now we are ready to conclude the test. And we will say step 4, 0 is less than or equal to anything. The level of significance was 0.05. So we have evidence, overwhelming evidence to reject H sub 0. So step 5, we will just write it down in a formal way that at least one of the p's is different, but the way we will write it down is following the language that we learned here. At alpha equals 0.05, there is enough evidence to reject the claim that, and please copy this down, all ages have crash rates proportional to their driving rate. Okay, so this is how another goodness of fit test looks like. I know it's different, but as long as you practice and you observe that you always have to make sure you have a number of categories and you have observed values in the first list and expected values in the second list, you should be able to answer many questions, real life situations, real life scenarios using this type of test, goodness of fit test. With this, I conclude the video.